Hello, my name is Daniel Bittman. Let me tell you about Twizzler, a new research operating system designed to realize the power of Unix in a world of highly shared, persistent data structures. Twizzler's design is based around our beliefs for how programs will evolve in the face of new byte-addressable non-volatile memory technologies, or NVM. First, we believe that NVM will fundamentally change our programming models and abstractions. We expect that programs will operate on in-memory data structures, thus necessitating persistent data references. Next, we believe that the OS needs to provide pervasive support for abstractions like persistent pointers in order to best enable simpler and more efficient programs. So let's have a look at some upcoming hardware trends. NVM is here. You can buy it today from Intel and throw it on the memory bus right next to your DRAM. The CPU can issue normal load and store instructions to it with a latency on the order of that of DRAM, which means that we now have a low latency persistent store that applications can get at directly. Moving persistent data up the storage hierarchy like this changes the way that applications can view and operate on data. In fact, they must change to take full advantage of what is being offered. The old way of getting to persistent data, where we would explicitly load it into volatile memory, deserialize it, compute on it, reserialize it, and then explicitly store it to disk, worked okay in the past. Disks were slow, and the latency of these operations was hidden, and we had to issue explicit block stores at some point. But when the latency of the persistent device is less than that of even a single system call, we can no longer afford the kernel interposition involved in explicit I/O. We can improve programmability as well. These operations encompass the lion's share of systems programming. Imagine how much useful work we could get done if we didn't have to do them. Imagine how much time we would save, both in program time, but also in programmer time, because we didn't have to worry about maintaining multiple data formats and the transformations between them. Imagine how much easier data sharing can be if the data is always in one format, as opposed to constantly moving around this cycle. Persistent memory offers us this world, but only if we take the steps to change the key abstractions that the OS provides, and to change applications to best take advantage of this new technology. We need to start treating persistent data like it's memory, not like it's storage, because in this world, it is memory. And don't worry, we have a compatibility story as well. Directly accessing persistent in-memory data structures has some immediate consequences. First, those data structures are persistent, which means we'll need some way of constructing long-term data references. Persistent data, by definition, outlives the actors that operate on it, either because that data is shared simultaneously across different programs or shared across time, that is, across invocations of the same program. Because persistent data has a lifetime longer than that of the processes that create it or operate on it, we cannot store any ephemeral context associated with those processes in the persistent data. This is a recurring philosophy. All of the context necessary to interpret data needs to be stored with that data. Let me describe what I mean by way of an example. Imagine we have some processes. Observe, process 1 and process 2. They want to share data, but that data has pointers in it. If this data structure is persistent, I can't just write virtual memory addresses into it, because virtual memory is by definition ephemeral. It's tied to the creating process. Instead, we must store a persistent pointer, one that is based on a more fundamental notion of data identity instead of an ephemeral notion of location. Building an efficient, persistent pointer design is a key part of our work. The second implication of direct access to persistent in-memory data structures is that the OS's responsibilities drastically change and reduce. The low latency nature of NVM demands that the kernel no longer be involved in the persistence path for the most part. Therefore, the kernel does not need to provide services for mediating access to persistent storage, and therefore no longer needs to act as mediator for things like rendezvous, communication, or naming. The kernel gets out of the way of user space, and many kernel bypass strategies naturally fall out of this. An example of removing kernel abstractions is a process. What is a process? A pile of threads, a security role, a virtual address space, and a bunch of kernel state, like file descriptors. But if we disconnect the virtual address space from how applications access data, and we no longer need things like file descriptors, a lot of that kernel state goes away, and we're left with no reason to couple a bunch of different abstractions like threads and security roles into a single process notion. Instead of mediating access to persistent data, the OS provides sufficient support for user space to manipulate all data as in-memory data, without needing to coordinate on some ephemeral context. We call an operating system data-centric if it provides this mediation-free access to data such that that data can persist. That is, all of the context necessary to interpret the data is stored with the data. We contrast these to process-centric operating systems, which instead focus on ephemeral actors as being the primary abstraction. Well, what about alternative approaches? Well, it wouldn't be OS research without talking about POSIX. The hallmark of POSIX is kernel-mediated I/O through explicit I/O calls like read and write, which already fails to meet our requirements because of the explicit I/O calls. But POSIX often also ends up forcing the programmer to think in terms of multiple data formats. Even mmap, which does admittedly help the problem somewhat, requires the programmer to still think in terms of virtual addresses. We could try layering support for NVM on top of POSIX. PMDK is an NVM programming library, which supports persistent pointer abstractions and runs on top of POSIX. But it doesn't provide a complete picture because it requires the programmer to work both in a POSIX world and in an NVM world at the same time, managing the complex interaction of features between both. An example of this is naming, and as we'll see a little later on, cross-machine sharing. Twizzler is a point in the bounded design space of data-centric operating systems. Twizzler provides low kernel involvement for applications accessing persistent data. It provides an efficient and flexible persistent pointer design, and provides a standard library of features necessary for effectively writing NVM-based programs. The execution environment in Twizzler is one in which there is little distinction between how threads access volatile and persistent data. Memory in Twizzler, both volatile and persistent, is broken up into objects, where an object is a flat region of memory containing semantically related data. The contents of objects can be directly accessed and manipulated by programs, and is of course largely application specific. Objects are also the unit of access control in Twizzler. An example of an object might be a B tree, but an object could just as easily have multiple B trees in it, and just as easily a B tree could be spread across multiple objects. It all depends on how the application wishes to do things. For example, an application might wish to have different parts of the tree protected by different access rights. Applications in Twizzler are supported by the Twizzler Standard Library, libtwz, which acts like a library OS similar as to an exokernel, and provides services for common object management and manipulation routines. The kernel provides management of physical resources, as well as multiplexing memory into objects and providing services for thread scheduling and thread synchronization. It also acts as the trusted computing base, servicing page faults and security violations. For compatibility, applications link to Muscle, a C library that we modified to run on Twizzler. We changed Muscle's system calls into library calls to our library Twix, which we wrote to support POSIX applications. Through Muscle and Twix, applications can operate on objects using POSIX functions, at the cost, of course, of explicit I/O. This is another key philosophy. Applications need to change in order to take best advantage of NVM. It is these applications that should get first-class OS support. Instead of building support for exciting new hardware by shoehorning in that support on top of existing ill-suited interfaces, we provide old software with compatibility layers and design the system for how new applications will be written. Okay, let's talk about persistent pointers. In Twizzler, objects have a unique 128-bit ID. Right now that ID is 128 bits in size, though we could increase it if necessary. To form the kind of identity-based reference that we've been talking about, we could take that object ID and combine it with an offset, and then be able to reference any piece of data within any object. However, just combining the ID with the offset would dramatically increase pointer size, and therefore have a significant performance impact. Additionally, we would limit flexibility, because application programmers would have to work entirely within these 128-bit IDs without any possibility of abstraction. So in Twizzler, we play the classic trick and add a layer of indirection. Every object in Twizzler has, at a known location, a data structure called the Foreign Object Table, or FOT. This table is an array of FOT entries, each containing the object ID of an external reference from this object. Instead of storing a pointer as an object ID and an offset, we store an index into the FOT along with the offset. Our pointers can now be 64 bits, but more importantly, this indirection opens the door to more possibilities. In FOT entries, we can store additional metadata, like protection information or ref counts, but we can also store names. Instead of relying on the file system to handle naming for us, we get naming through the core pointer framework of the system. These names can be resolved on pointer resolution, enabling late binding and allowing programmers to think in terms of human-readable strings instead of just object IDs. Let's talk through an FOT example. Check out object O here. O has an FOT and it has a pointer inside it. That pointer has FOT index of 1, so we can use that index to index the FOT and get back object ID A. We can then use object ID A and the offset to index within that object and get to the data. An FOT entry of 0 means that the pointer is an internal pointer. It references data within the object itself that the pointer resides in. I want to stress that the FOT is a per object and not system-wide data structure. This is a manifestation of our philosophy that all context necessary to interpret data should be stored with that data. Per object FOTs makes objects self-contained. So consider now, pointers and objects refer to data via identity and not ephemeral location, and object IDs are large enough to refer to any object in the world, and objects are self-contained. This means that I can share objects across machines, not just across processes on a single machine. If I copy an object from one machine to another, all the pointers mean the same thing. Let's contrast this with PMDK. So in PMDK, pointers are stored as an object ID offset pair, where the object ID in this case is 64 bits. Let's imagine we move an object from one machine to another. Well, the problem is that 64 bits is not large enough to ensure no collision in the object ID space. This means that we have to do one of two things. Either we have to coordinate ahead of time on the object ID space, which gets harder as we scale, or two, we would have to perform some fix-up operation on the receiving machine. The problem with this is that because the object IDs are stored inside the pointers, the fix-up operation is necessarily application-specific, adding complexity. In Twizzler, we can avoid both of these. We can avoid the global coordination and the fix-up operation through the use of indirection. In addition to providing a comprehensive persistent pointer framework, Twizzler provides basic services for coherency and consistency. Applications need to be able to write crash-consistent data structures in NVM. But the research is still in flux, and so we wanted to avoid prematurely prescribing a particular solution. Twizzler does, however, provide basic building blocks for cache line flushes, as well as a higher-level transactional log that can be used to safely persist data. Of course, Twizzler provides a security model designed around NVM. Briefly, the removal of the kernel as mediator means that the kernel has to be able to trust security policy coming from persistent data. To accomplish this, we use cryptographically signed capabilities to define security policy and access rights. Additionally, since the kernel is not involved in much of the persistent data access, the kernel uses the MMU to do much of the security enforcement of the system. More details on this, as well as when access rights are bound to threads, for example, are available in the paper. Twizzler's implementation is a relatively small system written in C and C++. The design choices that we've made result in a relatively small kernel that is still capable of supporting a full user space. More design details, for example, how we use virtual memory hardware, are available in the paper. Twizzler itself is open source and is available right now at twizzler.io. In evaluating Twizzler, we wanted to highlight the programmability features. Our first goal was to demonstrate the benefits and simplicity afforded novel applications written natively for Twizzler. Our second goal was to show that existing applications can be easily ported to Twizzler. I want to stress that our goals are programmability and not performance. Of course, advances in programmability need to come without a significant performance impact. And of course, we do expect to see some performance improvement due to the simplification of software layers that the Twizzler model provides. Our evaluation consisted of writing a key value store, or KVS, with some NVM-focused requirements, and porting SQLite to Twizzler while changing its storage backend to use Twizzler abstractions. Let's talk about the KVS case study first before going into the performance tests. We built a simple KVS in C for Twizzler. Twizzler's model allowed us a few convenient, simplifying design choices here. First, we were able to hand out direct pointers to data. When performing a lookup, instead of copying the value out to a temporary, we were able to hand out a direct reference to it because of Twizzler's flexible pointer model. When working with persistent memory, avoiding unnecessary copies is important and natural. Second, we separated the index and the data into multiple objects. Twizzler's pointer model allows us to construct cross-object data references with no more complexity than constructing an internal data reference. Thus, the additional complexity required by managing two different namespaces in a single linear address space, as would be the traditional approach, is no longer justified. This means that, for example, we could change the organization of the index structure in a factored way without needing to rethink the global layout. Next, we extended the requirements of the KVS to support access control. In Twizzler, this was easy. Instead of storing all values in a single object, we store them in multiple data objects according to access policy. Since cross-object pointers are natural in Twizzler, adding support for this required almost no modifications to the KVS code. When performing a lookup, I may get back a pointer to data, but if I'm not allowed to see that data, I won't be able to dereference it. Consider the implications here. Often security is an end-to-end thing implemented at the hardware level, the system level, and the application level. Sometimes, of course, this is unavoidable, but what a win it is when an application can reuse lower-level security features without having to re-implement them itself. Compare this to a Unix approach. We implemented a similarly featured KVS on top of POSIX interfaces. We found that the extra complexity involved in managing paths significantly increased code complexity because Unix doesn't support a pervasive notion of cross-file references. Furthermore, we weren't easily able to extend that KVS to support access control like we did in Twizzler. Because of the way that mmap works, we would have needed to know ahead of time all of the accesses to be made, or would have needed to remap all of the objects on the fly, each adding their own flavor of complexity. For existing software, our goal was to port a relatively large application. SQLite is a commonly used local SQL implementation with a B-tree-based storage backend. We ported SQLite to Twizzler, replacing the B-tree storage backend with Twizzler-based red-black tree code. Note that the rest of SQLite remained untouched, demonstrating that our compatibility layers are effective. We ported SQLite to Twizzler in 2 steps. First, we found a port of SQLite that used LMDB as its storage backend. LMDB stands for the Lightning Memory Map Database, and it uses mmap to access persistent storage. We took the LMDB port of SQLite, and then we implemented enough of the LMDB API on top of Twizzler abstractions to get SQLite to run. In this process, we discovered that Twizzler's pointer model actually makes a lot of the interfaces in these KV stores obsolete, because they were just largely wrappers around pointer operations. We compared our port of SQLite to Twizzler to 3 other SQLite implementations running on Linux. The first was unmodified or native SQLite. The second was SQLite ported to use LMDB as its storage backend. For the third, we took the Twizzler LMDB interface that we wrote and converted it to use PMDK instead as its storage backend. All of these tests were run on Dell servers using real Optane DIMMs. Our first experiment used YCSB, a common benchmark, to drive the database. This graph shows normalized throughput, so higher is better. We found that Twizzler was faster in all instances, while PMDK's implementation was often slower. Of course, Again, performance was not our primary goal here, but here we see the effects of the simplification of software layers. For the second experiment, we compared the latency of issuing queries against an existing million-row database. Here we see the results. This time we're looking at normalized latency, so lower is better. Here, PMDK was significantly worse in almost all tests, while Twizzler was similar to the others. Note that we're comparing two highly optimized B-tree backends to two fairly straightforward red-black tree implementations. We attribute the performance difference between Twizzler and PMDK to Twizzler's pointer operations being more efficient, and also to PMDK's doubling pointers in size, which has a significant impact on cache performance in pointer-heavy data structures. Twizzler is, of course, still under development in many ways, but one of the directions we're most excited about exploring is placing Twizzler into a distributed environment. The global namespace of object IDs can be truly that, global. Because Twizzler has pointers based on identity and not location, moving data around a network can be done much more easily, even to the point where we can easily manifest either computation or data wherever they may be needed, changing the focus of distributed programming away from manually marshalling data around computers and instead describing more clearly what the computation needs to be. We're very excited about Twizzler, both in sharing it with all of you, but also in where we can go with it. We hope to have gotten across 3 key points in this video. First, this technology is coming, and it has the potential to greatly change our programming models. We want to be ready for that. Programming has always been about data, and we have an opportunity now to make our abstractions really reflect this. Second, the time for a new OS is now. Not just because of NVM, but this greatly accelerates the need, but because new applications built in new ways deserve first-class OS support. Compatibility is a vital feature, to be sure, but the primary abstractions provided by the operating system are not compatibility. Finally, working with persistent data on NVM naturally means that we'll be working with persistent in-memory data structures. These structures will need ways of accessing and understanding data that don't rely on ephemeral context. If we get this right, we have an opportunity to have a fast but also flexible persistent pointer implementation that allows us to open our data up to a global address space. So, this is a new OS. It's a rare and risky endeavor. But we believe that it's the right thing, not just for a future with NVM, but for any future centered on data as the primary citizen. But of course, the test of a new OS is how well it supports innovation and how well it excites people. So we would love it if you read the paper and gave us feedback. Thank you for getting to the end. I would like to quickly thank my co-conspirators, Peter, Pankaj, Darrell, and Ethan, and my lab mates for their unending support. We're really excited to share this work with you. Thank you for watching.